Hello. So after the last video, the second one where we went over every single variable and made a decision whether to include or exclude, and also keep a record on why we are doing what we're doing, and also we put a few variables in. So we had a list of predictors that had missing values, and some of them had a lot of missing values and some of them had a few. So these are things that I will later look into them and see if there is anything, if the missingness has anything to do with the values of the other variables. Because if the missingness had anything to do with the values of the other variables, then that means that the missing is not random. And if it's not random, then whatever conclusion we make from this data is going to be biased. Okay, so it will increase the bias. So this is just something to keep in mind, but for now we ignore it. Okay, because we already have a lot of variables, so we're okay with removing as many as we can. Then we remove some categorical variables due to imbalance. They were categorical, and um, most of the observations would fall in a few of the categories. And there were some variables that we, for different reasons, inconclusively removed, so these are to be discussed. And there were some redundancies. Okay, here we create all terms, which essentially is all the variables we handpicked, and this is our response, and these are the variables we handpicked. Some of them are categorical, and we make sure that they are coded as categorical, and then it's all here. And then from now on, we will just use this. This is the full model, and yeah. So let's just go through it line by line. NAs, we talked about this. The problem is um, the columns of X are linearly dependent, and therefore this we can't really solve this, and that's why the linear fit model also has this problem. So we have too many variables. We need to do some sort of variable selection. Okay. Now we can use the library Leaps, and then we can try to do um, best subset selection. Okay, and to do best subset selection, that's what. Just keep it there. We use the reg subset function from the Leaps library, and yes, and we get an error because exhaustive search will be slow. To begin with, we know subset selection is um, take a lot of time because it needs to look at 2 to the power of p sparsity patterns. This many models need to be fit to go through all the options. The options of having all the models which include no variable, models that include one variable, models that include two variables. So models that include one variable, we have p of them. Models that include two variable. So what is this? and choose K. Do we have such a thing? Never mind. So you have P, then you have P times, it's essentially, let me just find this. Okay, so we need this library, basics, which I don't have. So let's just install it. Okay, and then reload it. Oh, okay. Okay, never mind. It's P plus, if this is this function, and choose K. So P choose 2 plus P choose 3 plus, you know what I'm trying to say. It's 4 plus P choose P minus 1, choose P plus P choose P. And this will be to the power of P. So this is as many we have to do, and we can't do it. It's impossible. So what we can do is we can say, okay, just try the best models with 4 variables. Which still would take a lot of time, but let's just run it. So you see, it's only trying to find models now with up to 4 variables. It took this much time, and okay. So the third variable that entered was Maureen. Let's see what is the first variable. I'm curious. What is the first variable that enters? Okay, prop diabetes is the first variable, and then education is the second variable, and Maureen, which was the third variable, and then neighborhood is, I think, the fourth variable. And what is the fifth variable? Yes, Maureen is the third one, and education. And now here's interesting. This is very interesting. So we are looking at models with so the first row, nothing is selected, right? Nothing is selected. Nothing is selected. None of these are selected. Okay, and then here we have prop diabetes. So if you wanted to, the model with the lowest residual sum of squares with only one variable will be the model that includes prop diabetes as the only single variable. So it will be simple linear regression with this. Now when we go to models with two variables, we have to look at the second row, and the second row has education and it has prop diabetes, right? And then there shouldn't be anything else in any other second row. Okay. Okay. So model with one variable is prop diabetes. Model with two variables, it's prop diabetes and education. And let's see what's modeled with three variables. So we're looking at the third row, and the third row we have Maureen. Okay. We have prop diabetes. We have prop contact diff. Whatever this is, we have to look into it. But the interesting thing is that um, the best model with three variables is prop contact diff, prop diabetes, and Maureen, whereas the best model with two variables is prop diabetes and education. So a greedy method, which would just add them one by one, would probably end up with education category and prop diabetes, and then the third one it will add something else, but it will never get rid of education cat. So this is a big difference between best subset selection, which is what we really want. We want to find combinations of covariates that together tell a story that can't be captured by each of them individually and by no other group of variables, more or less. Okay, and here is an example where we go from two variables to three variables, and suddenly a variable that was important among all the was the most important among all the models with two variables with degree 2 is not important among models with three variables, because now we have combinations of three variables that can express the data much better. So this is a phenomenon, just to be aware that this exists, but and that's the problem of greedy methods of backward and forward, because when they enter or remove a variable, then they're stuck with it till the end. And then there are some solutions for that, which is hybrid method, which add variables and then at the end looks back and sees, okay, now I added, so is there any one among these that I can remove? Okay, so we'll get that to that. But anyway, so we have this here, and then let's see, what is this object? I'm just curious about this object. What do we have here? That's the data. We have the residual sum of squares. For what are they for? Residual sum of squares of what? Okay, so for different degrees of freedom we have. Okay, but this was the RSS. So yeah, these residual sum of squares, each of them corresponds to one of the models. I don't know exactly which one, so we have to look into this function and read the documentation. That information exists, but we don't need it at the moment, so I don't want to go that route. But we take the summary of it, and the summary picks only the minimums. So when we have the summary, then these are the variables we have. So for example, reg summary, which it shows where each of them is entering or leaving. Okay, and then we have the residual sum of squares. The residual sum of squares increases as we add more variables. Okay, as we add more variables, the residual sum of squares obviously increases. And then we have RS sums. Wait a second. Sorry, this was the residual sum of squares. This is the R square, sorry. The R square increases, the residual sum of squares decreases, obviously. That's not surprising. More variables, better fit. What we care is about the CP or the BIC or some sort of cross-validation. But here we see that both of these measures, they decrease too, right? It's not that they decrease and then increase. It means that we have to go more than 4 or 5 variables to find the minimum, the tipping point. Remember, there was always this U shape that we had for the test error. We always wanted to find the degrees of freedom that gives us the minimum test error. But the test error required infinite amount of data from an oracle that generates data, and we don't have access to it. So we said, okay, there are 2 approaches, and both of them are trying to estimate the test error. One is cross-validation. The other one is some adjusted training errors. And the adjusted training errors, they is CP, which is some sort of AIC. It's essentially AIC, and then we have BIC, and then we have summary adjusted R square. And adjusted R square, BIC and CP are, you can think of them, well, BIC and CP, you can think of them as surrogates for the test error. The test error that we don't have, we can use CP or BIC to estimate it. They come from different assumptions. More or less, they tell the same story. BIC tends to be more conservative in the sense that it will give more sparse results.